In the previous video, we met up with the Schrodinger equation and looked at ideas about operators and how to use them to extract values for observable physical properties, energies, momentum, things like that. Okay. Today, in this video, what we're going to do is we're going to apply those ideas to a fairly simple problem that describes what's known as a free electron. Right? A free electron is essentially one that can go, well, anywhere it wants to, pretty much. What would make that the case? It means that the potential energy does not depend on the position, right? So we're going to stick with a one-dimensional problem here. So we're going to just take our problem to be a function of one coordinate x, and we're going to just say the potential energy v of x is just going to be a constant, what pretty soon we'll just call v, okay? Our Schrodinger equation is as written here. We still have our kinetic energy term in front, minus h bar squared over 2m second derivative. Then we have v times psi, and do all that, we're supposed to get back e psi, right? Where I probably should have written psi on the right as psi of x again, since I did on the left-hand side. I'm just going to claim that one solution to this equation is the wave function psi of x is e to the I kx, which, if you remember, we actually did a couple of things for that wave function. In the previous video, we used it to find values of energy and momentum from that, just because it was a nice simple wave function to work with. Okay, so first up here, we're going to verify that that's a solution. And then we're going to solve for what would K be in terms of E, the energy, and V, the potential energy, right? When it says verify that it's a valid solution, to do that, all we really have to do is take our proposed wave function, e to the I kx, and insert it into the Schrodinger equation and make sure that what we get back is some constant or collection of constants times the original wave function psi. So let's do that. So this is what I've got here for my my Schrodinger equation on the top. My wave function that has been proposed is just e to the I kx. We actually did the front part of this thing we did in the previous video, where we found that the kinetic energy for this particular wave function was minus h bar squared over 2m. Okay, or minus h bar squared over 2m times k, or yeah, I'm sorry, I'm saying this wrong, but let me just write it down and then I'll get it right. If I do this, when I do this, I'm going to get on the front end, I have the minus h bar squared over 2m from the operator. When I do the second derivative of e to the I kx, what I get is minus k squared. And all of that is still multiplied by psi. My potential energy function here, instead of being v of x, it's just going to be a constant v. So I'm just going to label that as v, and that's multiplying psi. And when I do all that, I want all that to be equal to e psi. All right. If I take that and just take the term in the front and take this part, that part is, so this will give me h bar squared k squared, my minus signs will drop, over 2m plus v. It's all of that times psi, and that means that this piece here is equal to my energy, right? That says it is a solution, because when I did that, in that front piece, the piece in the parentheses, we don't have any x's, right? And that's the thing that's important, right? All the x terms are gone, and so that collection of things there is in fact constant for constant v, and everything else that's in there is just an actual physical constant. So now I want to take that thing and I want to rearrange it so that I can solve for k in terms of the other properties. If I do that, I'll get k squared is equal to 2m over h bar squared. And then I'll have e minus v, right? If I take that, I could take the square root of that. That'll give me k equal to square root of all that stuff. And all that I could also write as I could say, I could say that all that is also equal to the square root. If I wanted to, I can replace E minus V with saying that's the kinetic energy, because E is the total energy and V is the potential energy. So I've got H bar squared, and I've got what I'll write here as E sub K for the kinetic energy. All right, so that gives me what I set out for. That says that that's the value of K in terms of the things that are in there. I've got the mass of the particle, I've got the total energy and the potential energy. Okay, where I just wrote the last one in terms of the kinetic energy because I'm going to use that result in something else a little bit later on. All right, so as I've said, that is one solution, and we've now proven that, e to the ikx. There are other solutions, right? There are other ways we could solve that equation. That just happens to be the simplest looking one, and so it's the one that we've picked to start with, and we have that description for what k is. Note that in the previous video, we also found the momentum for this, this wave function to be h bar times k. Right? We didn't say it was for a free electron at that point, but we did just say, well, if the wave function is e to the ikx, what's the momentum? And that's what we got. All right. So let's think about what this this wave function might actually look like. To do that, a simple way to understand that this thing is wave-like is to take this and write it in trigonometric terms, okay? So I can take that e to the ikx and I can express that in terms of cosine and sine terms, right? This is just a little bit of that manipulation of complex numbers, okay? If I do that, I get a real part of my wave function, which is just cosine of kx, and I get an imaginary part, which is I sine of kx. That says that both pieces of my wave function are going to oscillate, be wave-like. They're going to vary, and they're going to repeat when kx goes through multiples of 2 pi, right? Because kx is the argument of both sine and cosine in there. And so in this plot, we've drawn the real and imaginary parts, I guess, where the real part is the cosine, and so it's the dashed line, right? So this is the real piece, and this is the imaginary piece. But they both have wavelengths, if you will, of 2 pi associated with them because of that, right? And so in that form, it's much simpler to see that e to the ikx function is basically is a traveling wave, right? That's a way to describe that thing from there, okay? If I want to take that periodicity idea a little further, I can say that the wavelength of that thing in both cases, it has to be 2 pi, right? Because it's the argument of sine and cosine, right? So if I set x equal to where a wavelength comes, then I know that in my actual function, the argument of the sine function is kx, right? So I want to set x equal to lambda, then I can write kx is equal to k lambda, and I know what k is, right? Because k is this quantity here, that's what we found before, and I can set all of that then equal to 2 pi, right? If I do that, I can use this to get a sort of roundabout way to arrive at proving that this is consistent with the de Broglie relationships. Okay, so let's do that. I've got that expression up here, which says, let me solve that for kinetic energy. If I do that, I've got the kinetic energy in there. I'm going to take it and I'll solve it for kinetic energy to the 1/2, I guess, because that's what I've actually got in there. And that will do just fine, right? The kinetic energy from this thing is equal to 2 pi h bar. So keeping kinetic energy to the 1/2 from here, I'm multiplying the h bar squared from there up to here, right? And so when I take this h bar to the square root of it, I just get 1 h bar there. And then on the bottom of this, I'm going to have 2m still to the 1/2 power. and I'm going to have my wavelength lambda. Okay, little bit of cleanup on there. I can get rid of the 2 pi and turn the h bar just into h. If I do that, then I've got 2m to the 1/2 and lambda here, right? If I take that, the other thing I'm going to do is I'm going to say that we also know from good old classical physics that the square root of the kinetic energy should be equal to the square root of p squared over 2m is kinetic energy, right? So if I take all of that and take the square root of it, I'd get the square root of kinetic energy, and that will give me p over the square root of 2m, right? If I combine those two things, I could say that I get p over square root of 2m (1/2). So my pen doesn't work as well near the edges of the screen, I think. And then I get h over square root of 2m lambda. And when I do all that, that will give me that p is just equal to h over lambda, right? Which proves that our argument here and the wave function we've got are also consistent with the de Broglie relationship, which said that we could connect up the wavelength of something that we think of as a particle in terms of its momentum from that, okay? So what do we know about our free electron, right? We have said that its position, its potential energy does not depend on position, right? And that would seem to argue that it sort of, in a general sense, doesn't matter where it is, right? Its energy is independent of its position, right? If I want to think about where it's supposed to be, what do I want to do? I want to take the probability density function, which is the square of that wave function, right? I have an I in there, and so when I square it, I have to do the complex conjugate, right? If I do that, what I get when I square my wave function is I get e to the ikx times e to the minus ikx. That gives me e to the 0, and that's equal to 1, okay? So that says psi squared is the same for all values of x. What that tells me is that I know nothing whatsoever about where this particle is, right? So in this case, knowing the wave function does not localize the particle at all, right? This is different from, gosh, at the start of the previous video, I had up there those pictures of orbitals, and I had one in there that was the density plot for the electron distribution in a hydrogen 1s orbital, right? And there were places where the electron was more and less likely to be. In the case of our free electron, it really doesn't matter where it goes because its energy doesn't change as a function of position, right? So the reason why we can say things about the distribution of electron density in an atom is because the potential energy of the electron does depend strongly on where it is, because it depends on the charge interactions between the electron and the nucleus. So that's an odd result. It says that quantum mechanically, there's nothing we can know about where the electron is in this particular case, right? Because there are no limitations on where it can go. Its position is well and truly undefined. But we could sort of work around this in a curious way. We can take a wave function and make another wave function by taking linear combinations of allowed states, right? You've kind of sort of thought about this principle without knowing it when you talk about things like making hybrid orbitals, like in organic chemistry. If you talk about the structure of benzene and say we're going to make sp2 hybrid orbitals to make the planar geometry, right? So our free electron, the simplest case, the potential energy doesn't depend on position. The simplest case is just to define that constant potential energy as 0. Right? You always get to pick where 0 of potential energy is anyway in any kind of problem, and if it's never going to change, by far the simplest choice is just to call it 0, right? Then my total energy is just my kinetic energy. We proved that e to the ikx is a solution. It turns out if you do that same manipulation using e to the minus ikx, that also works, right? And so those are 2 of many possible solutions. If those 2 are solutions, then any linear combination of those 2 has to also be a valid solution to the wave function, Okay, so that says I could write a wave function that looked like this one here, right? Where C1 and C2 are just two weighting coefficients. They're essentially saying what are the fractional contributions of those two terms to my overall wave function, right? We can think of this as being a combination, or a sort of fancy word for that is it's a superposition of wave functions, right? And so we've created a new state, which is the linear combination of those first two, what I've labeled down here as psi sub k and psi sub minus k. Those k and minus k's there would be what are known as wave vectors for those solutions in again, somewhat fancier terms than we perhaps really need to do this. What does that do for us? It actually begins to tell us something about where the particle wants to be. It turns out that once I make this superposition, now all positions are no longer the same. Let's look at how that would work. So I'm going to take and set the two coefficients equal. I'm going to say I want to make a linear combination that's essentially 50-50, right? It's equally likely to be e to the ikx and e to the minus ikx, all right? If I do that, I can use this relationship here, right? And do that on my two pieces. And if I do that, my wave function comes out to look like this. And your authors walk through this in the textbook as well. But I get terms like this. And if we look, we can see that I get a cosine term over here and a cosine term over there. Those are both positive, so they reinforce. I get an IC1 sine term here, but then I get a minus IC1 sine term over there. So those two terms are going to cancel. When I do that, my linear combination gives me now a wave function that has only the cosine piece. And among other things, that means my wave function is now real, right? The imaginary component of my wave function has been knocked out by taking this linear combination, right? One way to think about this is the two wave functions are interfering with one another, right? So I have two wave functions, they're both repeating with this period being the same, right? And if we do that and we put them in the same region in space, then they should interfere. The wave function we get from this is now no longer an eigenfunction of the momentum operator. How do we know that? The momentum operator has what in it? It's got a single derivative term in it, right? If I take the derivative of cosine, I get sine. I don't get cosine back again, right? And so that says I changed how it depends on the x variable so that it says it's not an eigenfunction, right? So my momentum is no longer specified for this. If I look at the wave function, I can see that it should look something like this, right? So now it's all real. I don't have to do the imaginary component or anything. So my wave function psi looks like this. It still repeats at 2 pi, right? So this is the cosine function, so it starts at a maximum over here. When I get to 2 pi, I get back to the next maximum, right? If I take psi and square it, I don't have to do the complex conjugate anymore because my wave function is real. Now I get a function that looks like this one down here, right? This is now psi squared. That's my probability density. So now there are places where the electron is likely to be, where the maxima are, and there are places where there are what we'd call nodes, places where the electron is forbidden to be, down there at the half integer multiples of pi, right? So what has happened here is now we know something about where the particle is, but it turns out we don't know its momentum anymore, right? Because the momentum no longer, the wave function is no longer an eigenfunction of the momentum operator, and that says its momentum is no longer specified, right? So in this superposition of the two wave functions, with a single solution, I knew the momentum exactly, right? The fact that the momentum was the wave function was an eigenfunction of the momentum operator says if I measure the momentum of an electron described by that wave function, each and every time I'm going to get that momentum value, okay? In that single wave function, just e to the ikx or e to the minus ikx, I get to know nothing about the position, right? So I know everything about the momentum, but nothing about the position in that case, right? In the case of my superposition, with two wave functions in that linear combination, I lost knowledge of the momentum, right? Because if you actually, we'll look at in the future a way to find the average momentum of that state, and it turns out to be 0. Very loosely speaking, the reason for that is the e to the ikx wave function and the e to the minus ikx wave function. They correspond to the electron moving in opposite directions from one another, right? So if one of them is going this way, then the other one is going that way. With the coefficients the same, those two things are equally likely, right? And that means that your momentum will either be plus or minus that quantity, depending on the instant of the measurement, right? So when we did this, we lost knowledge of the momentum because we used to know the momentum as a fixed value, right? It was an eigenvalue. Now it's not. We gained some knowledge of position because we used to know nothing about position, and now we know that there are some places where the electron is more and less likely to be. If we made a more complicated linear combination, we could make a combination of many different solutions. If we did that, we could gradually get to know more and more about the momentum as we let more different wave functions interfere with one another, right? There would be destructive interference in more regions, and we'd build up the probability in the place where the interference was constructive, right? At the same time, we would lose more and more information about momentum from doing that, right? So this is our first brush up against what we will later formally define as the uncertainty principle, or this idea that we cannot know the momentum and the location, or the energy and the location of our quantum particle at the same time. Right? That's important for things like electrons in atoms, and that's why we have come to settle for this depiction of electrons in atoms as being represented by these diffuse clouds of negative charge, and not as something that says, no, the electron is just there when it's in that particular orbital, right? Because orbitals basically just don't work that way. All right, that concludes this relatively little video. We'll come back to this free electron problem again going forward once we have a couple of more tools at our disposal for evaluating things. We'll talk next time about things like normalized wave functions and expectation values.